Okay, let's unpack this. We're doing a deep dive today into genetic medicine, specifically looking at the delivery problem. It's a huge bottleneck. So our mission is really to get our heads around how large language model, the tech behind things like ChatGPT, how they're fixing these massive issues with viral vectors.
And that constraint is massive. It's genuinely what holds things back right now. We lean heavily on AAVs, adeno-associated viruses.
Yeah.
They're kind of the go-to carriers, non-replicating standard stuff. But the problem is anywhere from like 30%, maybe even 70% of people, they already have antibodies. The therapy gets zapped instantly. And trying to design one vector that's safe, hits the right target tissue, and is cheap to make, historically that's been, well, basically impossible, an intractable optimization puzzle.
Right, intractable. So if the old way is just slow, expensive chemistry like trial and error,
Wow.
is the big shift really just thinking about the biological sequence, the actual proteins
Or-
as a language?
Precisely. Yeah, that's the core idea. We're using specialized models, protein language models, for de novo design, which means instead of slow discovery, you get fast generative computational design. So, for example, AI can engineer, say, an oncolytic virus. It can make it express specific enzymes, like hyaluronidase. This enzyme actually degrades the physical goo, the matrix inside solid tumors, the ECM, so the virus spreads much better. And this is designed on a computer, not found by chance in a lab.
Okay, so the AI redesigns the biology. Does that same kind of optimization thinking carry over into manufacturing? Because that's always been a major cost issue for gene therapies.
Oh, absolutely. It connects directly. The LLM approach feeds right into QC and making production more efficient. We're seeing integration with new tech now, like mass photometry. It basically weighs individual virus particles, so you can instantly tell empty shells from the full therapeutic ones really fast.
Wow, and the cost comparison you mentioned.
It's kind of mind-blowing, like maybe $5 a measurement compared to traditional methods. Those can run up to $2,000 per sample.
Okay, that's something I think, Dermot. That's not just saving money. That fundamentally changes who can even afford to play in this space, right? It lowers the barrier. So if AI slashes design time and manufacturing costs by like 99%, how does that rewrite the playbook for companies actually developing this tech? What's the business strategy look like?
Yeah, it leads to a really smart hybrid model, balancing risk and reward. On one hand, you've got the high upside potential, a licensing model for the core AI platform itself. Think big pharma deals, milestones, royalties, big potential payouts. But, and this is crucial, they often pair that with a steadier fee-for-service CDMO operation. Custom development, manufacturing for others. That provides consistent revenue. It's the engine that funds the really long-term, high-risk R&D without being totally dependent on the next big licensing deal.
That structure makes a lot of sense strategically, but isn't there a risk? Does the CDMO side maybe dilute the value of their unique AI platform?
That's a fair question. But the sources seem to argue the real value is protected by just how good the AI is, how effective the designs are. And that's exactly why regulatory trust becomes so incredibly important. The FDA, for instance, they're not just rubber stamping this. They have a 7-step risk-based framework. It's for assessing the credibility of these AI model outprints.
Right, credibility. Here's where it gets really interesting. The big hurdle everyone talks about is the black box problem. If the AI suggests a brilliant sequence, how do you prove it wasn't just, a lucky guess? How do you trust it?
Exactly. And the solution emerging is explainable AI, or XAI.
Yeah.
LLMs have these things called attention scores built into them. They're part of how the model works.
Yeah.
XAI uses these scores to basically create a trail. It shows why the model picked a certain sequence over others, so you can align the AI's reasoning with known biology. It proves the design wasn't magic. It was, sophisticated, understandable engineering.
Okay, so what does this all mean? What's the big takeaway for you listening?
I think the core message is that this AI-native approach directly tackles the fundamental market need. It allows designing vectors that are, right from the start, inherently easier to manufacture, safer to use, and more effective. It solves that delivery problem that's held back genetic medicine for so long.
And maybe the final provocative thought to leave you with is this. The sources we looked at really argue that being proactive here, embracing transparency, using XAI, working within that FDA framework, it's not just about jumping through regulatory hoops. It's actually becoming the key competitive advantage. It's what you need to build trust, secure those crucial partnerships, and actually bring these potentially life-changing therapies to market.